Good evening, everyone. All right, so hope all of you had a good recess week. Okay. So for today's lecture, what is going to happen is we are going to be uh, finishing up on the MIPS part of the module. All right, by having a quick recap on data part, and then we're going to go on the control block. And once we're done with that, we will review the tutorial. And the tutorial is also a good way for us to revise the whole data part and control block together. All right, and then we will get to see how everything comes together and allows us to execute our instructions. Okay, and then after that, we will review the term paper that I released, and so that everybody is clear on the expectations, okay, on what is required for the term paper. Okay, so give me a minute. I will share the screen and then we can get started. Okay, so today's lecture, we're going to start off with the control block. Okay, so we're going to be looking at the control signals that are needed, okay, in order to make sure that the correct data passes through from one stage of the processor to the next stage. Okay, so before we get into that, all right, so let me just do a quick recap of what we covered the week before the break, all right, on the data part. Okay, so that we all have a quick revision and then we can go on to control block. Okay, so let's look at this instruction, which is the add. Okay, add 8, 9, 10 over here. So from this instruction, we know that register 9 is your RS, register 10 is your RT, and this is your RD. Okay, so we understand from this instruction, okay, that you want to take the contents of register 9, take the contents of register 10, add them together and put the result in register 8. Okay, so that is what this instruction is. Okay, so that is the assembly language instruction. So the first step is, from the assembly language instruction, we want to be able to translate it into the actual machine code, correct, the ones and zeros. Okay, so for that, we have to refer back to our earlier slides where we talked about the instruction format. Okay, so the instruction format, this is a R-type instruction. So for R-type instruction, we have a particular positioning of bits. So regardless of the type of instruction, we know that the first 6 bits is always the opcode. Okay, and then for R-type, it is RS, RT, and RD. Okay, and then we have a shift amount and a function field. Okay, so these are all the different parts of the instruction. Okay, so instruction is 32 bits, and we break up that 32-bit instruction into different, or to represent different parts of an instruction, okay, depending on the format of the instruction we are dealing with. All right, so in the previous lecture slide, the data part, we looked at this type of R-type instructions, we looked at a branch instruction, we looked at a memory access instruction as well. All right, so if you're still not very sure on that, don't worry. Okay, later when we do the tutorial, I think you'll have a good recap of all the different type of instructions and what is happening. Okay, so from this instruction, when we translate it, okay, so we can get the opcode. Okay, the opcode and the function field are things we get from the data sheet, which I have shown you before. RS, RT, RD basically is referring to the register numbers we're dealing with. So this is 9, all right, this is 10, and this is 8. Okay, and shift amount is 0, not used when it's not a shift instruction. Okay, the first thing that you see in our design is the register file. So the bits of RS go into RR1, which is read register 1, and the bits of RT go into read register 2. Okay, so when we send these two sets of information, that means we are sending a value 9 here and you are sending a value 10 over here. All right, so when we do that, what happens is the register file will process this information and give us the content of register 9. and the content of register 10 on both RD1 and RD2. Okay, and after that, what happens? All right, so we have our, okay, so before we go to the next stage, we know that in this instruction, after we do the addition operation, we're supposed to write back to RD. So RD is specified in these bits over here, 15 to 11. So we need to go through a multiplexer over here because of the fact that we are having the need to support the I-type instruction as well. Okay, so in the I-type instruction, the RT bits are the actual destination register bits, correct? Whereas for R-type instruction, the RD bits are in the 15 to 11 position. So because of that, we need to have a multiplexer here. Okay, so this multiplexer, if you recall, I mentioned that it is just a mechanism where you have multiple inputs and you can select which one is passed to the output side. So in this particular instruction, we know that the register we want to write to is register 8. Okay, so since this is register 8 is represented by these bits here, this is what I want to select and pass through over here. Okay, so that is where the multiplexer comes in, and in order for that to happen, register destination, this is basically the control pin, okay, which we are going to be looking at in more detail in the lecture. So these control pins or control signals are the ones that will decide which data from the input of the multiplexer gets channeled to the output of the multiplexer. Okay, so in this case, okay, for this instruction, I need to make sure that register destination selects the bits that are on the second entry over here. Okay, and those bits are passed over as the write register to the register file. Okay, and similarly, you see that for the ALU, okay, in order for me to do the addition operation, I need to pass this information to the ALU. So register 9 contents and register 10 contents both have to go to the ALU. So register 9 contents, no problem, they are directly connected. But for register 10, again, it has to go through a multiplexer. Okay, again, this is because we have instructions with immediate values. So those immediate values have also to be supported. All right. So that is where the multiplexer comes in. So the multiplexer over here, all right, has another control signal here called the ALU source. Again, as the name suggests, it basically decides the source of the ALU data. That means, do I take the data coming from the register file, or do I take the immediate value over here? Okay, so if it was an R-type instruction, which is in this case we are dealing with, I want the data that is coming from the register file. Okay, so what I want over here is, I want this data to be passed through to the next stage. Okay, and then you have your ALU block. So ALU block will perform the addition. So how does your ALU block know that it must do an addition? So again, that comes back to some other control signals here. Okay, so we must be able to tell the ALU based on the opcode and the function field and so on, that this is an addition operation. Okay, so the ALU will perform this operation for us, and then I have the result. Okay, the ALU result, and as in this case, the ALU result is the actual value I am looking for. All right, if it was a memory access instruction, okay, then the ALU result is actually the address, okay, that you're dealing with. But in this case, it's the R-type instruction, so the ALU result is what I really want. Okay, that is the addition of the contents of register 9 and register 10. Okay, so that data will come out over here and is connected to this multiplexer here. All right, and since this is the data I want for this multiplexer, this last multiplexer here, I must be able to channel this data through. So this data will come all the way back here, okay, to the write data pin. And since the write register has already been selected to be register 8, I will be able to write back to register 8. Okay, so this is basically a quick recap of what we did in the last lecture. But of course, in the last lecture, we went into more discussions and different type of instructions as well. Okay, so if you haven't seen that e-lecture yet, please make sure you do it. All right, so then when you look at that and this lecture together, you will have a complete picture of how everything comes together. Okay, so this is just a quick recap. So now what we're going to be focusing on is all of these control signals. Okay, so we know we have all these control signals, and we need to make sure these control signals have the correct values for the different type of instructions we are dealing with. Okay, so the register destination, register write, and so on. Okay, so these are all the signals that we saw just now. So let's go through them one by one and see how we can configure them so that they behave correctly. All right. Now, the whole idea, like we said just now, is we want to make sure that we have the ability to channel the correct information to the next stage. All right, and the correct information must again, it depends on the type of instruction we are dealing with. All right, so let me come to the next slide here. So for the control block, okay, this control block, so all the while we were dealing with this particular design. So now what we are doing is we are now introducing the control block inside. So this control block, what does this control block do? It is basically in charge of generating all these signals for me: the register read, register write, ALU source, and so on. Okay, all these control signals that you see, okay, are generated by this new hardware block, okay, which we call it the control block. Okay, now what the control block must do is it must be able to take in the information. All right, okay, and which is very much, okay, two things. One is the opcode, okay, and the other one is the function field. All right, we're supposed to take in this information from the instruction, and using this information control the various signals so that the multiplexers have the correct values to pass the data through. So let's go ahead and look at how to do this. Okay, so the first step we need to do is go back to our instruction format. Okay, so if you look at our instruction format, we can see that for R type instructions, okay, let's say like add, subtract, and so on, we have this particular format here, okay, which is standard for R type. That means you have 6-bit opcode, RS, RT, RD, shift amount, and function field. Okay, so for all R type instructions, we have this format. When you look at I type instructions, what do you see? You see that you have opcode, RS, RT, and then the remaining 16 bits is the offset. Okay, and this is basically based on the memory access, or in the BEQ instruction is the offset from PC plus 4. Now, let's look at the first control signal here, the register destination. Okay, the first control signal here. Now, for this control signal here, you can see that we are labeling it such that the top is 0 and the bottom line is 1. Okay, so this is the labeling we are following for this multiplexer here. All right. Now, when the signal over here has a value of 0, what happens? That means whatever is on top will pass through. Okay, whatever is on top will pass through. So what is on top here? So you can see that on top what you have is the instruction bits 20 to 60. All right. When my signal here is a 1, when the signal here is a 1, what will pass through? Whatever is on the bottom line over here. Okay, so what is in the bottom line here? It is the instruction bits 15 to 11. Okay, so this signal that we're going to generate, which is the register destination here, okay, what will happen is when it is 0, whatever is at the top line will go through. When it is 1, whatever is at the bottom line will go through. Okay, so that is how the multiplexer is labeled and it will work. All right. Now, similarly for register write, as you can see, is not connected to any multiplexer, but it is basically a signal to tell the register file whether we need to update any register. Okay, whether we need to update any register. So if it is 0, that means I do not need to write to any register. When it is 1, a new value will be written. Okay, so when will a new value be written? Okay, so of course all Rtac instructions, you will update a register at the end of the instruction, correct? Similarly, a load word instruction, because a load word instruction also has to take data from memory and update a register. Okay, so Rtype instructions and load word instructions are the ones that will have the register write activated. So that tells the register file that for this instruction, I'm required to update one of the registers at the end of the instruction. Okay, the next is your ALU source over here, which is this. So this ALU source, okay, has two inputs. Again, one is your RD2, which is connected to the top line, and the other one at the bottom line is the immediate value, the sign extended immediate value. All right, so top is 0, bottom is 1. So when it is 0, the data that pass through is the data from the read register data 2, okay, the RD2. If it is 1, then the sign extended immediate value will pass through. Okay, so for almost all the multiplexers, we will follow the same convention where top is 0 and bottom is 1. Okay, but only one multiplexer is reversed. Okay, later you will see. Okay, but for all the rest, the top line is always considered the 0 line and the bottom line is considered the 1 line. Okay, next is memory read. Okay, so memory read and memory write, again, they are not connected to any multiplexer. They are basically to tell the data memory whether you are going to do a memory access or not. Okay, so if the line is activated, that means it's 1, that means I'm going to do a memory read. If it is 0, then you're not doing any memory read. Okay, similarly for mem write, if it is 1, that means I am updating a memory location with new data. Okay. If it is 0, then I'm not performing any write. Okay, in this instruction. Okay, so the only multiplexer where the sort of numbering is in reverse order or swapped is the last multiplexer here, which is the mem to register. Okay, so for this multiplexer, we have a 1 on top and a 0 below. Okay, and it is just to be aligned with the naming of the register of this multiplexer. So when you say mem to register means we want to take the data from the memory to the register. Okay, so when it is 1, then it is true, we are taking the data from memory and putting it to the register. Okay, when it is 0, then the data is the ALU result. Okay, so the 0 is this line here. It's whatever coming out through the ALU. Okay, so that is the mem to register. And then the next one is this, the PC source. This PC source is again to differentiate between two possible locations for the next instruction. So by default, okay, whenever you fetch an instruction from memory, you already generate PC plus 4. Correct? That is the address of the next instruction you want to fetch from the instruction. The other possible option where you do not go to the next instruction is if you're going to take a branch. Alright, so the branch is of course calculated through the immediate value here. Okay, that is sign extended. Okay, and that result is over here. Okay, so this PC source, okay, will be based upon, okay, the decision of whether the branch is to be taken or not taken. All right, and this actually is leveraged from this is 0 bit in the ALU. Okay, so this is 0 bit, okay, tells us whether the branch is to be taken or not. Okay, so why is this signal a bit different from the rest? Okay, for all the other control signals, you can immediately know the value when you already fetch the instruction. Correct, whether it's an add instruction or add I instructions or anything like that. But the moment you fetch the instruction, okay, you will immediately know all the control signals. Okay, but if let's say I fetch a BEQ instruction, okay, 1, 2, and I put a 4 here. Okay, that means the branch will be taken, okay, if register 1 and register 2 are the same. Correct. So when I fetch this instruction, I know that this is a branch instruction. Correct. So that's the first thing. But I do not know at that point of time whether I'm going to take the branch or not, because I still need to do this check. Okay, I still need to do this check to confirm whether the content in the registers are the same. Okay, so when you fetch the instruction, you know it is a branch, but you still do not know the decision on whether to take the branch or not until the equal or not equal computation has been done. Okay, and that is only available, or that result is only available when you complete the ALU stage. Okay, when you complete the ALU stage. So I need to wait for this E0 signal to be generated from the ALU block. Okay, and then together with that and the fact that we know if it is a branch instruction, then I can decide on what goes to the next PC. That is what comes out of this multiplexer here. All right, so that is where we need to do this operation. Okay, so we do not go through all these low level logic gates. Okay, but basically what you need to know for this is basically what we call an AND gate. Okay, which is drawn with this symbol. Okay, and an AND gate, if you look at the truth table, okay, so if I give you two inputs A and B, and this is X. Okay, for AND gate, the truth table is very easy. Only when all the inputs are 1, the output is a 1. Okay, the moment any input is 0, the output is going to be a 0. Okay, so this basically tells you that all inputs, okay, must be true. Okay, then output is true. That is the basic operational AND gate. All right, so in this design over here, okay, what you are basically seeing is the control unit must first tell me that it is a branch. Okay, this part we know, correct? Because this information we get it from the opcode. Okay, the moment the control signal gets the opcode information, it automatically knows that this is a branch instruction. The other information we need to confirm whether the branch is to be taken or not is this E0 information, which is coming from the ALU. So when both this information is true, okay, that means it's a branch instruction and it's also 0, then I can go ahead and take the branch. That means the address that will go to the next or the next address of the instruction to be fetched from is coming from here. Okay, so that is your PC source. So that is again slightly different from the other control signal that we saw, because the decision of the control signal is only available after the ALU completes. Okay, so it is basically either PC plus 4 or PC plus 4 plus the sign extended left shift by 2. Left shift by 2 is equivalent to multiply by 4. All right, so this is again, you can look back at our earlier slides on the assembly language programming. If you recall, whenever we do a branch instruction, the compiler will put in a number which corresponds to the number of lines of code. Okay, but each line of code is 4 bytes. So we need to multiply by 4 to know the actual number of bytes that we need to offset. Okay, so this is something we looked at in the earlier slides, okay, when we're looking at the assembly language programming. Okay, so these are the basic things of the control signal, okay, that we need to look at. Okay, so we have all of this that we have reviewed. All right, so the thing that we are not going to go into detail is the ALU control. Okay, so the ALU control, okay, this ALU control is we're not going to go into how this ALU control is actually generated. Okay, so if you look back at this ALU control, okay, what the ALU control does is it actually is responsible for telling the ALU unit what operation that is supposed to carry out. All right, is it an addition, is it an AND, is it an OR, or so on. All right, and we're not going to go into that alone because that requires you to go into more lower level hardware. That means how to connect different logic gates together and come up with a particular truth table and K-map matrix. So since we did not cover all of those stuff, okay, we are not going to go into that for this chapter here. Okay, so what basically you can see that the ALU control, okay, is a separate unit that will be in charge of providing the correct signals so that the ALU is able to do it. Okay, but we don't need to worry about that as long as you understand the rest of the control signals, okay, that we have covered. Then you more or less understand the whole flow of what is happening. All right, so basically in this slide here you can see that we have the full data path and control signals needed in order to put everything together and execute the instructions that we have been seeing so far. Okay, so let's have a quick look at the output signals that we are going to be generating. All right, so for Rtac instruction, okay, register destination we say is 1. Okay, why is register destination 1? Because for Rtac instructions, your RS, RT, RD, this RD here is the register that we're supposed to write to. Correct? That means this is the information that we want to channel here. All right, because for Rtac instruction we have RS, RT, RD, and RD is the destination register or the register that we want to do the write back to at the end. So that is the bits, or those are the bits that must be channeled to the write register pin over here. Okay, so that is why register destination is 1. So you have to remember that all the multiplexers, the top line is 0, bottom line is 1. The only different one is this, the last mem to register, where the top is 1, bottom is 0. Everything else it is 0 and 1 here. Okay, ALU source. Okay, ALU source is selecting between the register data or the immediate value. So for R type there is no immediate value. Okay, there is no immediate value. So what you will get is this 0 is what we want to channel through. So that's why it is 0. So we looked at this, we looked at this. Now map to register. Okay, so again for R type instruction, okay, there is no memory access involved because we are dealing with the two source registers. Do the ALU and we want the ALU result to write back to the register. So this is the part we want. So for this register, we want a value of 0. Okay. Now register write has to be a 1 because for Rtac instruction. So if you look at any Rtac instruction, add, okay, 4, 5, 6. So we always need to write back to the destination register. All right. So the register right here has to be a 1. Okay. Mem read and mem write both must be 0 because we are not doing a memory access. All right. Branch will be 0 because your control unit will know that this is not a branch instruction. Okay, Rtac instruction is not a branch instruction. All right, so we will have to set branch to 0. Okay, this ALU op, okay, you can ignore this part here. Okay, we are not going to cover ALU op here. Okay, now for load word instruction. Okay, so let's look at load word instruction, okay, and understand how all this works here. So let me erase all of this first. Okay, so for load word instruction, the register destination. Okay, so if you look at a load word instruction, load word. All right, so you're taking the data from a memory location, okay, and then you are trying to take this data and you are trying to write it back to a register. Okay, so this operation here, what is happening over here? We are actually doing an addition, correct? And this addition is the addition between the contents of the register and the immediate value of 4, correct? Okay, so for this case, what you have is your RS is given, okay, and this is your RS and this is your RT. All right, so your RT is the register that you want to write back. So this is the one that we want to channel here as a write register. Okay, so in this case, we want the line on top. So since the line on top is 0, the register destination multiplexer has to be 0. Okay, so before I carry on, for this R type, does anybody have any questions so far? Okay, of how I got the ones and zeros on the first line. Does anybody have anything that you want to ask or clarify about how I filled up that first row? Okay, R type is basically any instruction where the two source registers, the information is coming from two source registers and the destination is also a register. So that's what we call R type. Okay, load word and store word, they are what we call the I type instructions. Okay, including the BEQ. The rest are all the I type instructions. Okay, so let me go on to the next one. Okay, the load word. Okay, so we just look at the register destination. So the ALU source is this multiplexer is to decide which data is channeled into the ALU. All right. So if you look at it, for this case, what I want is the RS register with this immediate value. The immediate value. So the immediate value is this one, the 16-bit sign extended and coming through here. Okay, so since I'm taking the lower or the second line, that is 1, correct? Because top is 0, bottom is 1. So that is why here has to be a 1. This is 0, this is 1. Here, this is also 0, this is 1. Okay, so for this load word instruction, okay, what will happen is you will have to take this ALU result, and this ALU result is going to point to a memory location. We're going to point to a memory location, and we want that data is to be read out, and that data, okay, is the one that is going to be returned back to the register. So what we want is the line on top to be channeled through. So that is 1, this is 0. That is why this multiplexer has a value of 1, because for this last multiplexer, the 1 is on top, 0 is below. Okay, and since a load word instruction requires you to update a register, correct? Because we are going to write back to a register at the end of the instruction. So this register write must be 1. So you're telling the processor that you are going to do an update to the register at the end of the instruction. Okay, and for this instruction, we are doing a memory access, and in this case, it's a memory read. So memory read is 1, and memory write is 0. And we're not doing a branch, so branch is 0. Okay, so that is the load word instruction, okay, and the sequence. Does anybody have any questions on this load word sequence that we just saw? Okay, so for load word, we are taking the data from memory and transferring it to a register, correct? So the only operation we are doing is we are reading from the memory and updating the register. We are not doing any write to the memory. So that is why mem write is 0. Okay, so for the next instruction, store word, for store word, we are taking data from the register and updating a memory. So in that instruction, you will see that mem write is 1, but mem read is 0. Okay, so it depends on what instruction we're doing. For load word, we are taking from memory to register. So it's only a read access. For store word is from register to memory. So it's a write access. Okay, mem to register. Mem to register is basically the multiplexer that decides which of these two data goes back to the register file. Correct. So there is two input. Okay, the one on top is from the memory. The one at the bottom, okay, the one at the bottom is from the ALU output. All right, so one of this is to go back to the register. Okay, so for load word, you can see that I'm accessing this data. Let me change. Okay, so I'm accessing this data here, and this data is basically the content that is in a memory location. So the memory location is calculated based on the data in register 3 and offset of 4. So that addition is done by the ALU and that points to the address. Now that data, so this address here, okay, let me call this address X. So somewhere inside here, there is an address X here. So that data is now coming out here. All right, and I want this data to be actually written into register 2. So this data must be channeled back, okay, to be written into register 2. So that is why we need to select the top line. Okay, for mem to register multiplexer, the top line is labeled as 1, the bottom line is labeled as 0. Okay, the mem to register will be 0, like in the earlier instruction where we are doing a R type. If you are doing only a R type, okay, what we are interested in, like this instruction here, when we're doing R type, okay, when you're doing R type, the to source is register and the data from the ALU, because for this instruction, okay, add 456, we are basically doing an addition here. And this addition is from the ALU, and the ALU result is the one that is going to be written back. Okay, so that is when mem to register will be 0. So we are not interested in anything coming out of the memory. We are only interested in what is coming out of the ALU. Okay, so in this case, the register write is only referring to the write, which is to update the register. Okay, mem write and mem read is depending on whether you're doing a load word or store word. If it's a load word, mem read will be activated. If it's a store word, mem write will be activated. Okay, so it depends on whether it's a load word or store word. Okay, so let me show you the store word. Okay, then you will see the difference. Okay, let me erase this first. Okay, so now let's say I do a store word. All right, so okay, maybe I use a different number here. 8. Okay, so when I do a store word, what is happening here? Okay, so for a store word, let's look at the control signals and try to make sense of it. Okay, so firstly, register destination. We have put a X over here. Why is it an X? All right, because for a store word, what are you doing? You are taking the content of the register and we are writing it to a memory location. We are writing it to a memory location, and this memory location, the address is content of register 3 plus the offset of 8. All right, so in a store word, we are taking the data in the register and writing to a memory location. Okay, now register destination, if you see here, is a multiplexer that controls which of the bits go to right register. All right, and we say X. When you say X in logic design, we say it's a don't care. That means it doesn't matter whether it is 0 or 1. And why doesn't it matter? Okay, why it doesn't matter is because your control unit will set the register write pin to 0. So this register write pin will be set to 0. So when the register write pin is set to 0, even if you have anything on the right register pin, even if you have anything on the right data pin, it makes no difference because you are not able to write anything, because the register write pin, that is the main control signal that gives permission for you to update a register file. Okay, so if that main control signal is already 0, you will not be able to update any register. All right, so because your register write pin is going to be set to 0 by the control unit, it doesn't matter what my register destination multiplexer value is. So that's why you put an X over here. Okay. For ALU source, we say it is a 1. Okay, why is it a 1? Because this information here, all right, is the addition of so this information here, the address we are writing to is the addition of the register and the immediate value. Correct? This is the immediate and this is the register. This is your RS and this is your immediate value. Okay, so in my case, or in this case here, what we want is the ALU to perform the addition, and the addition is through the RS content, which is register 3 content, with the immediate value. Okay, so that is why you want the ALU source to be a 1. On top is 0, below is 1. Okay, now let's look at this mem-read and mem-write first. Okay, then I come back to mem to register. For mem-read and mem-write, so in this case, a store word instruction is to take the data in the register and write to memory. So it's a memory write. So that is why the memory write is 1 and memory read is 0. Okay, because this is a store word instruction. Okay, so what is happening here? What is going to happen here is I'm taking the data. Okay, okay. So this data coming from where? This is your RS. This is your RT. Okay, so if you look here, there's actually a line, okay, that is going from RT, okay, which is RD2, going to your right data. Okay, and your RT is specified here. All right, this is your register. In this case, this is your 4. So 4 comes here means the content of register 4 will come out here. and that is what is going to be transferred as the write data. Okay, so for a store word instruction, we are taking the data from the register and writing to memory. We are writing the data to memory. Okay, the address, okay, this is the address. This address is already obtained from the ALU result, correct? Because we have provided the RS over here and the immediate value over here. So when both of them add together, that gives me the address of where I'm going to write to. And the data is coming from the RT, which is the RD2 over here. Okay. So once I reach this data memory stage, once I reach the data memory stage, it's already considered I complete my instruction already, correct? Because my objective was to update the register, sorry, to update the memory with the new content, and I've already updated it, correct? Once I complete my data memory block here. So this mem to register again has no significance. Okay, again, why is it so? Because this mem to register is to decide who or which data goes back to the register file. So one of this is supposed to go back to the register file to be updated. But like what we just discussed, the register write is already 0. Okay, register write is already 0. So it doesn't matter whether some data from the top line goes back or some data from the bottom line goes back. It doesn't matter because your main control signal, which is register write, is already 0. So nothing will still be returned to your register file. Okay, so that is why your mem to register is also a X over here. Okay, and finally your branch, we're not taking a branch here, so your branch is 0. Okay, so that is your store. So you can see the difference between load word and store word. For a store word, you can see that some of the registers can be set as X, all right, because other control signals have sort of a higher authority because they are the main uh, deciding block. Okay, so the X is basically again to give us the idea that you can, it doesn't matter because some other control signal is overriding it. All right, so don't worry, when we look at the tutorial after this, we will again go through the questions, okay, which are very similar to this, and then you can see it again why the X is there and how the whole flow comes in. All right, then I'll explain again in detail why the X comes, okay, for some instructions, whereas for other instructions you need to have explicit ones and zeros. Okay, now let me just go on to the next instruction, the BEQ instruction. So again, for this BEQ instruction here, okay, you see that, okay, so for example, the BEQ instruction, BEQ, let's say 1, 2, and a label next. Okay, so if 1 and 2 are the same, I'll branch to this label next. Okay, now, okay, so let me not put a let me put a number so we can see that a bit more easily. Okay. Okay, so let me erase this part here first. Okay, so for a BEQ instruction, what will happen? You are not going to update any memory. You are not going to update any register, correct? Because a BEQ instruction, the main objective is to decide what should be this, what should come out of here. Okay, whether it's PC plus 4 or PC plus 4 with the new offset, okay, taken into account. All right. So that is the main objective of BEQ. So there is no update to register. There is no update to memory. All right. So in that case, you can see that firstly, your register write is going to be 0. So when my register write is going to be 0, that means I'm not going to update any register. Your register destination value doesn't matter. Correct. So that is why this is the X. All right. And similarly, since there is no memory access, this mem to register output also doesn't matter, because whatever goes back here to write data is also not going to be returned to any of the registers, because your register write is 0. So that is why this is also a X. Okay. And in this case, you have, this is your RS, this is your RT. Okay. So both of them will go through here. Okay, so you have your RS here and RT here, and we are going to do a comparison on the register, on the content of both these registers. So what we want is the RS value to come here and the RT value to come here. So for this ALU source, top is 0, bottom is 1. So that is why the ALU source multiplexer is 0. And since there is no memory access, memory read is 0, memory write is 0, and it's a branch instruction, so only for this your branch is set to 1. Okay, so in order to understand this, of course, you really need to look at how data is flowing, okay, from one part of the processor to the next stage and the next stage and so on. Okay, then you will be able to relate that with how the control signals should be designed. Okay, so what I would, okay, so don't be too concerned right now. I'm sure you still have a lot of questions, all right, a lot of things you're not sure, but in the tutorial we're going to go through this exact same sequence, okay, with different type of instructions, and that will help you to reinforce all of these concepts. All right, so all your doubts, you just hold it there first. Okay, when we are going through the tutorial questions, I will again come through it step by step, and you can see what is happening. All right. Okay, so let me just finish up this topic here, and then we can go to the tutorial. All right, so for a single cycle implementation, so the next few slides is a bit on the timing aspect. So a single cycle implementation, all right, that means what they're asking us to do is, given this design, how do you calculate the time that it takes, okay, to do some access. So for example here, you can say that the ALU type of instruction, that means the R type instruction, okay, you will require access to the instruction memory, the read register, the ALU, and the register write. All right. For RTA instruction, as we saw just now, there is no memory access. If there's no memory access, I do not need to have any value here, because I don't need to access the memory. So it's only the instruction, the register access, the ALU, and then the final register write. Okay, for this type of load word and store word, there is a memory access. So you need to be able to have instruction memory access, register access, ALU, and data memory access as well. All right, but only the load word instruction has a register write as well. Okay, so if you remember your load word instruction, after I get the data from the memory, I still need to update my register one more time. All right, so it takes the longest amount of time. And finally, a branch instruction, you don't have a register write, you don't have data access, data memory access. So it's only the instruction memory, register, and ALU. Okay, so we will look at that again, coming back to the tutorial part. Okay, so these next two slides are just for your information. Okay, it's not covered in class, it's not tested. All right. One of the drawbacks of, you can see that when I fetch an instruction, I need to wait for this entire instruction to be completed before the next instruction can be loaded into the processor. Correct? That means you can basically say that each instruction, all right, is going to be limited by the slowest instruction. Okay, because I need to make sure I have sufficient time for the slowest instruction to execute, then every instruction can still complete on time. All right. So how do we improve this throughput? Okay, so one way is, or the two possible implementations that you can enhance this to. One is called multi-cycle implementation. All right, where you take a single clock cycle, all right, for sort of different stages of a system. All right, that is one option. The other is pipelining, where you put buffers in between each stage to hold on to data while it is being channeled through. Okay, so again, these are not covered, both multi-cycle and pipelining, they're not covered. All right, again, this is just to give you the idea of how these kind of things can be improved and how architectures are designed to be more efficient. All right, so basically the control unit and the data part unit all comes together, all right, to give you the complete processor. All right, so of course I understand it is not easy, okay, and it is again very different from many other modules that you have currently have experience with. Okay, so let's go through. Okay, let's go through the tutorial. Okay, right now. Okay, and then let me sort of reinforce. Okay, and use that to reinforce what you have seen so far. Okay, so let me bring up the tutorial. Okay, so I'm going to go through the tutorial with a PowerPoint slide with some good animation that gives you a nice picture of what's happening. At the end of the class, I will email it to you. All right, so you can have go through the slides yourself to see how this whole thing works. Okay, so I will not go through the actual tutorial handout. Okay, but whatever the questions that are there is basically asking you to analyze the whole flow. All right, given an instruction, all right, you're asked to analyze the flow of what is happening with each stage. Okay, what is coming, what is sent to the input of each stage, what is coming out at the output of each stage, what are the control signals involved, and so on. All right, so all of that I'll cover through these slides. Okay, and at the end of the day, I'll email this to you. All right, so let's go through this. Okay, so this is basically what we just saw. All right, that means the whole unit. All right, and all these control signals. All right, and now we're going to try to make sense of how all of this comes together with different types of instructions. All right, so this is the first instruction we're going to be dealing with, which is the load word instruction. Okay, so if you look at this load word instruction, okay, the very first step is what? The very first step is translating this instruction into the actual machine code. All right, so that part, okay, you should be able to do by now. All right, this is the opcode. All right, this is your RS, which is 15, and this is your RT, which is 24, and this is the immediate value. All right, so the first step that you must be able to do, okay, which we have covered in earlier lectures, is given an instruction, translate that instruction into your ones and zeros, right, into the actual machine code. Now, once that is done, you can take this entire 32-bit and fill out, all right, in terms of this over here on what is the opcode, the RS, RT, and so on. Okay, so in this case, this is basically what we call an I-type instruction. Correct, I-type instruction. So in I-type instruction, in this case, what we are doing is we are doing a memory access, and the memory access is given by what? Is given by this, the value of RS, which is this, add with the immediate value. Okay, so in our case, okay, what is going to happen? Okay, so let's go through and see step by step what is going to happen. So the first step is what is in RR1. So in RR1, the value here is 15. So the value that you see here is 15. All right, because read register 1 RR1 is directly connected to the bits 25 to 21. Okay, so the value 15 appears in read register 1. How about read register 2? Read register 2, what is the value here? The value here is 24. All right, because that is the RT bit location here. All right, so and that RT bit location is in 20 to 16, so 24 comes here. Now, why is 24 here in blue? Because in this instruction, we know that RT is actually the register that we're supposed to write back to. All right, RT is the register we're supposed to write back to. Okay, but it is still connected to RR2 anyway. All right, because that is the hardware design. All right, it is still connected to RR2 anyway, so it appears there. Okay, it appears there, but we know that because this is a load word instruction, the register 24 is referring to the register that we're supposed to write back to at the end of the instruction. Okay, so 24 comes to RR2, and at the same time 24 also comes here, all right, to the top of this multiplexer here. Okay, now what is going to happen next? Yeah, so this is what I mentioned just now. The red is the data that is used, blue is the data that is not used. That means it is there because it is already hardwired. Okay, some parts of your processor are already hardwired. Okay, so it will still be there, but we will always rely on the control signals to decide what is used, what is not used. Okay, so at the next stage, you can see that register destination is 0. Okay, why is register destination 0? Because I know that for this instruction, I want the 24 to be the one that is designated to be the write register. Okay, so that whatever is coming through on the top line, that means the line 0 is the one that I want to channel through as my write register. So 24 is also going to appear here. Okay, so all these control signals on the right that we see here are generated by the control block. Okay, so the control block, when it sees that this is a load word instruction, it will generate the control signal for register destination to be 0, which will allow the bits in position 20 to 16 to be selected to be the write register pins. Okay, so that is the first step. So the write register is now selected as 24, and that is what we are actually using that information for. Okay. Now, since we know this is a load word instruction, and at the end of this instruction, we are supposed to update the register, we can say that the register write is also supposed to be a 1, correct? Which we will see in a while. Okay. Now, what is coming here in the ALU? So in the ALU, the first operand 1 here is the content of register 15. Okay, the content of register 15. All right, so that comes to ALU 1. Okay, and register write just now, as I mentioned, is 1. All right, because we know that we are going to be updating the register at the end of the instruction. Okay, now ALU source. ALU source is set to 1. Why is ALU source set to 1? Okay, so let me change color here a bit. Okay, so now let's look at the ALU part. So the ALU, we know that the first operand is the data from register 15. The second operand is what? We know that the ALU is supposed to do a addition, correct? It's supposed to do an addition, and this addition is supposed to be from two different sources. One is the RS value, the register value, which is this. The second one is the immediate value. So I want this immediate value over here after it is signed extended to be selected as the second ALU operand. Okay, so because of that, my ALU source has to be a 1, the second line over here. So that is why the ALU source over here is a 1. So the operand 2 in this case, okay, for the ALU is actually 0. Okay, this 0 is because of this immediate value here. This immediate value here is 0. Okay, so this second operand is the actual immediate value. It is not from the register. Okay, it is the actual immediate value that is specified in the instruction itself. All right, so that is it. Now we are at the ALU part. Okay, so what is the actual address that we're going to be accessing? Okay, so the actual address is given by this, correct? Which is your addition of the content of your register RS plus the sign extended immediate. So this is actually, or this addition is the one that the ALU carries out. So this ALU result is the one that is giving me the address of where I'm supposed to get my data from. Okay, or where I'm supposed to get my data from. Alright, so that is why over here, the address of what I'm accessing is this. The content of register RS plus the immediate value. Yeah, the square bracket is referencing the data in the register. Okay, so the data in register 15, okay, which plus the sign extended immediate value. All right, when I add them together, that addition is done by the ALU. So that ALU result is the address that I'm pointing to. Okay, the address I'm pointing to. Okay, so for this is a load word instruction. So a load word instruction means you are doing a memory read. Correct? So mem read is a 1. Okay, and mem write is a 0. Okay, so in this case it's a load word instruction. So mem read is a 1, mem write is a 0. Okay, so now I'm reading from memory, correct? I'm reading from memory. So the data that I want is going to come out of the memory. It's going to come out of the memory. And this is the data that I want to channel back. Correct? So this is the data I want to channel back. So the mem to register has to be a 1. Okay, so mem to register has to be a 1. Okay, now let's look at this write data here, which has a value of register 24. It means the content of register 24. So what is this? Why is it in blue? All right. So for this, we go back to earlier on what we saw over here. We saw that the read register 2 has a value of 24 because your instruction RT bits, okay, the RT bits of your instruction have a value of 24. All right, but of course, in this instruction, we know that the RT bits is referencing the write register. Okay, but since it is also connected to read register, That means the contents of register 24 will appear here. Okay, the content of register 24 will appear on RD2, and that is also connected. Okay, so if you look at the line, this line is also connected to my write data. Okay, so that is why content of register 24 appears at the write data. But it doesn't matter, right? It doesn't matter because your mem write is a 0. So we are not writing anything to the memory. So even though something appears on the data bus, the control signal will tell us that we are not doing any memory write at this time. So nothing will be returned to the memory. Okay, but it will still appear there. Some data from register 24 will still appear there, but we are not going to be writing anything to the memory location. This is a load word instruction, so we're only going to be reading data from the memory. All right, so the data that we are reading from the memory is this, which is the address which is given by this and the content in that memory location. So that is what is going to come out of here. All right, it's going to pass through this multiplexer because mem to register is 1, and then it's going to go back here to the write data, bits of write data port of the register file. And since my register write is set to 1 and my write register is set to register 24, that means register 24 will now be updated with this content that I just read from memory. Okay, and since this is not a branch instruction, branch is 0, the ALU op, ALU control you can ignore. Okay, we're not covering that. Okay, so I know it's quite a lot to take in, right? Because you really need to understand and look at what is happening. So I'll stop for now and take any questions that you all have.
Sorry, can I ask if the RD2 is always going to write data? Because the overlapping arrows are a bit confusing.
The RD2 is connected to write data. The RD2
The
is
RD2 is also going to the ALU source multiplexer, right? That one
yes.
where we are deciding between the RD2 and the sign extended immediate value.
Yes. So the RD2 is only going to two places. One is going to the ALU source, okay, input 0, or it is going to the write data of the data memory. It's only going to these two places. Yeah, so this is one pathway for RD2, and this is the other pathway. Yes, it will go to both places at the same time. Okay, it will go to both places at the same time. But again, that is where the control signals come in. Correct? Over here at the ALU, at this multiplexer over here, your ALU source is set to 1. That means I will be taking the immediate value to go through to the ALU. Over at the data memory side, since my mem write is 0, it doesn't matter what comes here to write data. It doesn't matter because I will not write anything to memory. Okay, so you can see that there are many hardwired connections here. That means the data will go to many places at the same time. It is your control signals that will help us to decide what is used and what is not used, all right, and what goes to the next stage. Okay, so Memwrite and memread cannot both be one at the same time, correct? Then you're going to cause data corruption. Correct. So the idea is only one of it can be one depending on the instruction. Okay, if it is a load word instruction, only memread will be one. So yeah, that is the responsibility of the control unit. Right? If it is a store word instruction, then memwrite will be one.
Can I ask for mem to reg, right? Is something to choose between the memory, the data read from memory versus the result from the ALU, right? So that means if the mem to reg is 0, we are not even doing any mem. We don't care about the data memory result. So is there any relationship between the mem to reg and the mem read or mem write?
No, mem to reg will be needed whenever you are doing a memory read, correct? Because if mem read is one, then mem to register also has to be one. Because that means you
Yeah, otherwise you are reading, but then you don't bring it into WD, right?
correct. Okay, mem write, if mem write is one, then you are basically writing to the memory and it ends there. So mem to register will not be needed.
If you write to the memory, that means you are writing to the address that you gave to in the from the ALU result.
Yes.
But we are not updating any register.
Yes, because the only instruction that writes to memory is a store word. So for store word, there is you end the moment you write to memory. Okay, so let me just recap the control signals again, okay, so that everybody is clear what is happening. Okay, so let's look at the first control signal. Maybe I should erase. There are not too much arrows everywhere. Okay, so let's look at the first control signal again, which is the register destination. So the register destination here is set to 0. Okay, it's set to 0. That means I'm selecting the line at top. Okay, and what is the line on top? Line on top is having the data or having this information that is 24. And what is 24? In this case, for this instruction, 24 is referring to the register that I want to write back to. Okay, and the register I want to write back to is in the RT bits location. Okay, so since I want to write back to this register 24 and those and register 24 is specified in the RT bits location, I need to make sure that this register destination multiplexer selects those bits to be transferred to the right register selection here. So 24 will come here. All right, so that is the first thing. Okay. The ALU source again has two possible inputs, all right, which is to select between RD2 and the immediate value. For this instruction, we are going to compute the address based on the RS value and the immediate value. The RS value is automatically coming from RD1. Okay, so this is 15 and the data in register 15 is coming here. So this is your RS value. For this instruction, the second operand should be the immediate value. So this immediate value is coming from here. Okay, and for that, I need to make sure that ALU source is set to 1. Okay, so that is why the register destination here is 0. Okay, just now, and the ALU source is 1. Your ALU, what will it do? It will perform this addition for us, this addition, okay, to compute the address that I want to access. So this address will come out here. Okay, and once this address comes out, Okay, and since this is a load word instruction, your mem read will also be 1 and your mem write will be 0. So when mem read is 1 and I give an address, the data in that address location will come out of the read data line. Okay, and this is the data that I actually want to write back. This is the data I want to write back. All right, so since I want to write back the data coming from the memory, for the mem to register multiplexer, I take the line on top. So that is why it is A1. And where will I write back to? I will write back to the bit specified by the right register. And since the multiplexer here already says 0, it means 24 has come here. Okay, so the register I'll write back to is register 24, and the data that I'll write back is the data that is coming out of the memory. Correct, and the memory address is specified by RS, which is register 15, add with the immediate value. Okay, so that is how the whole thing sort of comes together. Okay, so I hope it is clearer now. Okay, so I think it's a good time to take a break, and now it's 8 o'clock. Okay, so let's go for a break, about 20 minutes break. You can, have your dinner, everything, come back, and then about 8:20 we will resume. Okay, I'll leave the slide as it is, okay, on the screen so that you can have a look at it and try to make sense and see if you have any other doubts that you still in your mind. Okay, so when we come back, we will go through the other instructions. Okay, and then you will see how the data will flow through different pathways. Okay, for different type of instructions. Okay, so let's go for a break first. Okay, I'll see you back here at 8:20. Okay, so I'll leave the screen. I'll just okay, so I'll see you back here in a while. Thank you. Okay, so welcome back. Okay, hope you all had your dinner and everything settled. All right. So let me go on to the next instruction. All right, so that we can see the different ways in which, okay, the processor is handling, okay, the data. So in this instruction, of course, once you execute this instruction, your PC is PC plus 4. That is a default, okay, because your branch in this case would be 0 because you're not executing a branch instruction here. All right, so let's look at this instruction, BEQ1312. Okay, so the first thing, let's look at what we know. So this will be your RS, RT, and okay, your RS, RT, and your immediate value here. All right, so this is the mapping, okay, to the registers. Now the next thing is, of course, translating this to your actual machine code over here. So opcode you can get from the instruction set. Then this is 1. Okay, so this is 1. This is 3. Okay, and this is your immediate field, and the immediate field here is 12. Okay. So the first thing is we know that 1 is directly mapped here. So value 1 comes here. So when a value 1 comes here, the content in register 1 will automatically come out of RD1, which will also be the operand 1 for ALU. Okay, so that part is always fixed, right, because it's all hardwired. And at the same time, what do you see? We see that 3 is coming here. So the value of 3 appears here and appears here as well. All right. Now for this BEQ instruction, okay, So let me go through step by step. So RR1 is 1, RR2 is 3. Now, register destination here is an X. Okay, why is register destination an X? Because for this instruction, BEQ instruction, the objective is to check for a condition and update the PC value. Correct. So we are actually interested in this. Correct. We're interested in this. That means whether the PC is going to be PC plus 4 or is going to be the new PC based on the branch being taken. All right. So there is no memory access. There is no update of any register. So that is why register destination is X, which means it could be 0, it could be 1. It doesn't matter because, okay, so that's why the right register bits here, we say is either 3 or 0. Okay, why 3 or 0? Because uh, 3 is what is coming into the line 0. For line 1, okay, this line over here is connected to the bits 15 to 11, which also happen to have a value of 0. Okay, so that's why we say it's 3 or 0, but it doesn't matter because register destination, okay, is not being used, and register write would be a 0. Okay, so since register write is going to be a 0, the register destination can be anything. Okay, it's not going to have any impact. For ALU, we saw that the RD1 is directly connected to operand 1. Correct. So the content of register 1 will directly map, okay, from the RD1 to operand 1. Okay, and ALU source. So in this case, the objective of the instruction is to perform a comparison check between the content of two registers. So for the ALU, the content of both the registers must go into the ALU. All right, that is what is needed here. So over here, what you want is this content, which is the content of register 3, to be channeled through to the multiplexer here. Okay, because the ALU is now going to do a check between the content of register 1 and the content of register 3. Okay, so that is why the ALU source is 0, because 0 is referring to the line on top. Okay, so the operand 2 for the ALU will be the contents of register 3. Okay, there is no memory access here, so both memory read and memory write are both 0. Okay, there is no memory access here. Now, the branch control signal here will be set to a 1. Okay, the branch control signal will be set to a 1. Of course, that is only one part of the branch, correct? If you recall just now, we said that this AND gate has two inputs. One is, of course, that the branch signal must be 1. The next is the is0. The is0 will tell us whether the branch is to be taken or not. So if it is to be taken, then we will set the PC source to be 1. Okay, if not, it will be 0. Okay, so ALU op, ALU control, no need to worry. And again, in this, going back to the register file, register write is 0. So if register write is 0, whatever comes into write register, whatever comes into write data, doesn't matter. Both we say is don't care. Okay, so that is why over here we say it is X. All right, here is also X, meant to register, because it doesn't matter whether the data from line 1 or data from line 0 goes through. Okay, because whatever data goes back, your register right is already 0, so nothing is going to be returned back to the registers. Okay, now the address here is given as 1 minus 3. Okay, why is it 1 minus 3? Because I mean the address here is given as content of register 1 minus content of register 3. Okay, why is that so? Because your BEQ instruction here is comparing the content of register 1 and content of register 3. Okay, and what your ALU does, okay, to do a comparison is actually it does a subtraction. Okay, it's just like in maths. If I want to compare whether x and y are the same, I can do a subtraction. And then I check whether it's equal to 0. Correct? If it's equal to 0 means they are both the same. Okay, so that is actually what the ALU is doing. So to do a BEQ check, it will actually do a subtraction and check whether the answer is 0. So the ALU result here is actually a subtraction result. All right, but again, because it is hard coded, you can see that the ALU result is hardwired to the address bus here. Okay, it's already hardwired to the address bus over here, so it will appear there. Okay, but it doesn't matter because memory write is 0, memory read is 0. So no matter what I put at the address bus, nothing is going to happen. No matter what I put at the data bus, also nothing is going to happen. Okay, so what is in the data bus over here? It is basically whatever is connected to RD2. Okay, so if you look at RD2 over here, RD2 is also connected to the right data. Okay, so that is why it's here. So the content of register 3 comes to the right data. Okay, so again, these are the hardwired parts of the processor, but the control signals help to reinforce what is to be done and what should not be done. All right, so since memrun and memread are both 0, whatever appears on the address bus of the memory or appears on the data bus of the memory is not going to affect anything. All right, so that is why they are both sort of some information is there, but it's not being used. Okay, and the write data is again the ALU result. Okay, that means this is either the ALU result, which is 1 minus 3, or some random value, because we do not know what the data could be there at the data bus, and we do not know what is the mem to register multiplexer input, correct? Because it is an X. Okay, so because of that, we cannot say for sure what is going to come out of this multiplexer, but it doesn't matter again what comes out because your register right here is a 0. All right, so the branch instruction, okay, what we are interested in is the computation of the branch address. Okay, the computation of the branch address is achieved where? Is achieved over here. That means where I take the lower 16 bits of the instruction, sign extend, okay, left shift by 2. This left shift by 2 is multiplied by 4. Okay, it's equal to multiply by 4 and add here. So this is your PC plus 4. Okay, so this is one option, PC plus 4, and that is the other option. So if you see down here, okay, maybe I'll erase this. Okay, so you can see here that the next PC value, okay, is actually either PC plus 4 if there is no branch, or PC plus 4 plus 12 times 4 if the branch is to be taken. Okay, so that is how we can see the flow of the data through the processor, okay, for this particular instruction. Okay, so again, I will stop and take questions that you have about this instruction, how it is being executed, or any part of the flow that you do not understand.
Mr. Ravi, can I ask for branch not equal? Can I understand how do we do it? Because, okay, so for BEQ, my understanding is we will compare the value in the RS address and the RT address, and we do a subtraction. If the result is 0, the is 0 is yes, and then the branch is 1, right? So you feed it into the AND gate. then it will be 1, right?
Mm.
So if it's branch not equal, how does it?
Okay, so the B and E we are not covering, okay, because that requires additional hardware over the side.
Understand.
Okay, so again, we are not covering B and E and other instruction like the jump instruction and so on, because that requires more hardware to be integrated in, which we did not cover. Okay, so for us, as long as you understand the BEQ and how the BEQ part works, that is enough. Okay, so does anybody have other questions about the flow and the control signals or anything like that?
What is PC source?
PC source is the control signal that will decide whether I take this one, either PC plus 4 or PC plus 4 plus the branch offset.
So in this case, if both RS and RT are the same, then PC source will be 1, right?
Yes.
Then we will advance to 12 times 4 plus the PC plus 4, which is
Yes.
25.
So if the branch is to be taken, then the address on line 1 is what I will go through. If the branch is not taken, then the PC plus 4 will go through.
So this is a little different from the previous examples because the sign, the control value of the PC source is determined after the computation.
Correct. So this one, that is why you need to add this AND gate, all right, because the other control signals, you know the value, okay, the moment you fetch the instruction. This alone you will only be able to know after the ALU part is complete. Okay, so okay, so mem read and mem to register controls read data. Okay, so mem read is when you want to read from the memory. Mem write is when you want to write to memory. The mem to register is basically to decide whether you want the data from the memory to go back or you want the data from the ALU to go back. All right, so that last multiplexer has two inputs. One is coming in from the ALU. The other is coming in from the memory. Okay, so this multiplexer will decide which data channels through to the output of the or channels back to the right data pin, okay, of the register file. Okay, so let me go on to the next instruction first. Okay, so in this instruction, this is a R-type instruction. So for this R-type instruction, basically you have RS, RT, and RD. Okay, and what you're supposed to do here is a subtraction. So you take the content of register 20, take the content of register 5, do a subtraction, and the result go into register 25. All right, so the first step is, of course, you put it all out in your binary format and you put it here. So you can see you have your opcode. Okay, you have your 20, 5, and 25. And then you have a opcode and a function field. Of course, the opcode and function field are both used for the control unit and the ALU control. And what do we know already? Right? So we can say that 20 comes here. That means the content of register 20. Let me. Okay, so the content of register 20 will come there. Okay, just give me a minute. Yeah, so the content of register 20 comes here, and 5 is connected to RT bit, so 5 comes here, and at the same time 5 also comes here. All right, and so if 5 comes to RR2, the contents of register 5 also will come out here. All right, so these are all fixed, correct, because they are already hardwired, so this will definitely happen. All right, and similarly for this first multiplexer, we can also say that since is the second input is connected to the instruction bits 15 to 11, which corresponds to the value 25, so 25 also comes here. Because all of this we know that will definitely happen. All right, so what is next? Okay, so we have RR120, RR25. All right, so the next thing is register destination. So what would be the register destination? In this case, we know that the destination register, which is the register you want to write back to, is the one that is specified by the RD bits. That means this 15 to 11 is the one I want to channel through. All right, so the register destination has to be a 1. All right, so that is the first thing. So the write register is now 25. All right. So for the ALU, the first operand is the contents of register 20. The second operand, okay, so this is R type, so both of the ALU inputs will be the register contents. So I would want the contents of register 5, which is RD2, to be channeled through as the second ALU input. Okay, so ALU source here should also be 0. This should also be 0. And since I'm going to write back to the register write is supposed to be a 1 as well. Okay, so that is what you will see here, 1 and 0. Okay, so operand 1 is content of register 20, operand 2 is content of register 5. And since we are doing a subtraction operation, okay, so since we are doing a subtraction operation, let me change the color now. Okay, so over here, what I will get is the content of register 20 subtract or content of register 5. Okay, so since this subtraction is the operation carried out of the ALU, that will come out of the ALU result. Okay, so that is the ALU result. But since it is hard-coded, so hard-wired to the address bus of the data memory, it will appear here. Okay, but we know that we are not using it, all right, because in our case there is no memory access. Okay, but since it is hardwired, it will appear there. Similarly, the write data, this write data is again hardwired to RD2, which is the contents of register 5. So that one will also appear here. Okay, content register 5. But we know we are not using it because both my memory and memwrite both will be 0. Okay, because there is no memory access involved in this instruction. So both of them will be 0. All right. And in this case, since we are taking the ALU result and we want the ALU result to be returned back to the register, so this ALU result that is coming out here is the one that should be channeled to go back. Okay, should be channeled to go back to the WD, the write data. That means your mem to register has to be a 0. Okay, and the data that is returned back, this data that is returned back is actually the ALU result, which is the 20 minus 5. I mean the content of register 20, subtract the contents of register 5. Okay, and there is no branch instruction, so branch is 0, and the other two you can ignore. Okay, so you can see that. Okay, definitely now when you look at this third instruction, you more or less get the hang of it already. Right, you get some idea of okay, what is happening at the instruction stage, the register stage, the ALU stage, and the memory data memory stage. All right, so I'm sure that when after going through these 3 instruction, it is a bit better, correct, compared to when we first started. All right, so you just have to go through these slides and understand again what is happening. All right, how data is channeled from one stage to another stage. Okay, and remember that certain things are hardwired, so it will still go from one place to another place, and the multiplexers and the control signals are the ones that help us to make the correct decision, correct, on what should go to the next stage. So that is the responsibility of the control unit. Okay, so does anybody have any questions about this instruction here? Okay, so the question to explain why write data is 5. Okay, because the write data here is this pin here. Okay, is connected. Okay, and it's again hardwired to RD2. Okay, it's hardwired to RD2. That means whatever is coming out of RD2 will automatically get channeled to this write data. And what is coming out of RD2, which is actually the content of register 5. Okay, so that will automatically come to this write data pins of the data memory. Okay, similar to the address. Okay, the address will have the value of register 20 minus register 5 because that is the ALU result. So that connection is also hardwired. Okay, but again, the address and data bus connections for data memory will not have any effect because memwrite and memread are both 0. Okay, so this 20, okay, so this numbers here 20, 25 and 25, these are the numbers that you take or that are encoded in the instruction. So when you write this instruction in your assembly language, all right, and you sort of compile it, it gets translated to the actual machine code, which is the ones and zeros. All right, so this 25 will appear here, 5 will appear here, and this is 20, 5, and 25. Okay, so it will appear here in terms of the actual register you want to access. All right, but from the instruction, we know that we are not talking about value 20 or value 5. All right, we're talking about the contents in register 20 and contents in register 5. So when I take 20 and I send it to RR1, I'm saying that I want the data in register 20. Okay, when 5 comes to RR2, I'm talking about the data in register 5. Yeah, so the bracket is basically referencing the data in that register. Okay, so we have 32 registers. Okay, and the registers can hold information for us. Correct. So when we write an instruction like this, okay, we are saying that we want to take that content, the data inside those registers, and perform some operation, and then take the result and put it in another register after that. Okay, so don't be too concerned. Okay, if there are still doubts, there are still things we can still discuss. Okay, so the marks, okay, all the multiplexers, okay, all the multiplexers by default, okay, it is 0 and 1. Okay, except for this mem to register alone, it is 1 and 0. Okay, and which one goes through, either 0 line or 1 goes through, depend on the control signal. Okay, so that is where all these control signals come in, all right? Because these control signals are the one that decide which one will be channeled through to the output. Okay, so that is the objective of the control signals. Okay, so memwrite and memread are basically to tell whether you are going to perform any memwrite or memread operation, correct? So you can say that if the memwrite is 0, that means if there is any data on the right data bits, okay, of the memory, you will not, it still doesn't matter, you will ignore them. Okay, you will not do anything. Okay, if your memory is 0, it tells me that I will ignore whatever address that is on the address bus. Okay, because I'm not going to output anything new onto the read data bits or read data pins. Okay, so I'm not going to perform any read access, or I'm not going to perform any write access if the mem read or mem write are 0. Okay, only if either of them is 1, then I perform that particular operation. Okay, if not, I do not do anything. Okay, so let me go on to the next question. Okay, so this question is basically on the timing analysis. Okay, so for this, basically what we are doing is we are trying to have an idea of how much time the processor is going to take, okay, to complete certain instructions. Okay, so inside your tutorial, the documentation and tutorial form, the different blocks have been allocated different timings. All right, we're supposed to analyze the total time that the different instructions are going to take. Okay, so let's look at this instruction here. So for this instruction, the sub instruction, for a subtraction instruction, we are going to, okay, so this one is what? This is the R type instruction, correct? The subtraction instruction is R type instruction. So we are going to take from the memory first. So we need to access the memory. All right, and then we're supposed to get the data out of the register files. So there is some time associated. So the first instruction memory, there is 400 nanosecond, and then another 200 nanoseconds. All right, but at the same time, all right, we also know that while I'm accessing the data from the registers, I also need to send my opcode, my function field, and so on over to my control unit, because the control unit is also responsible for generating all the control lines for me. Okay, so what do you see? You see that when the instruction is fetched in to the processor, different blocks get activated at the same time. correct? The register file also gets activated to prepare the data to come out. The control block is also activated to prepare the control signals, okay, to be at the correct value. Generally, register files are again sort of treated like a memory, all right, and memory access is usually quite slow compared to other type of uh, logic blocks. Okay, so control unit, though we didn't go into the details of how it is designed, it is designed using some basic logic gates, which we can say that they are much faster, okay, compared to memory type structure which is used in the register file. All right, so that is why the time that it takes for the control signal to control block to complete and generate all the signals is going to be much faster than the time it takes for the register file to complete and give me the data at the RD1 and RD2. Okay, so that is why we say that the control block is actually not on a critical path. Okay, what you want to do is you want to take the worst case scenario of all the different pathways in order for me to complete this instruction. Okay, so after I complete the register file, I have to pass through the data to the ALU, correct? So this ALU source, this timing has to be factored in because this marks will only take into effect after the data has been generated from the register file. So after the data comes out of the register file, then I have to go to the multiplexer, all right, and then I compute. So that's the ALU timing. Yeah, after the ALU completes, okay, then I pass through to this multiplexer, okay, to channel the data back to my register file. Okay, so for this R type instruction and sub instruction, there is no data memory access. Okay, so you don't need to worry about any access times for the data memory. So the main blocks are the first instruction memory, the register file, the multiplexer, the ALU, then another multiplexer, and then one more right back to the register file. Okay, so the total amount of time that is going to take is 980 picoseconds. So just now I said nanoseconds, it's picoseconds. Okay, so that is your sub instruction here. How about your load word instruction? Okay, so for your load word instruction, the first part is the same, correct? Because you have to fetch an instruction from memory, you have to pass through to a register file, okay? And as you pass through to a register file, okay, you can see that I have RR1, RR2, plus I have a write register. Okay, now the write register. So if we look at the timing here, after register file, I go straight to ALU. All right. Now let's look at this for a while first. For my after my register file, I have RD1. Okay, so my load word instruction. This is load word. Okay, so for example, register 1 for register 2, something like that. Okay, so in this type of a load word instruction, what is happening is you are taking the content of a register, add with the immediate value, putting back into a register. All right. Now, if you look at the arrows that we have drawn so far, we see that this part here we understand already, correct? Because the control unit, we said just now that it is going to be much faster than the register file. All right. And so it doesn't matter for me to include the control unit because I still need to wait for the register file. Okay, like I said, we are looking at the worst case scenario. That means what are the slowest pathway, or what is the slowest pathway that I will end up taking in order to execute this instruction. Now, for my write register, okay, in this case, let's say register 1, there is a multiplexer here. Okay, but I did not factor in the multiplexer. All right, similarly over here, For my immediate value, there's also another multiplexer here, but I did not factor in the multiplexer, okay, in my calculation so far. Okay, so again, why is that so? Okay, why is it not included? Okay, what? So the first thing is this first multiplexer here, this register destination. Why it is not included is because we only need to perform. Okay, so this multiplexer is to select which register I'm going to write back to, correct? And that information, that write back operation is only needed at the end of the instruction. Okay, so even if in the beginning there is some delay by the time it reach here, it doesn't matter because I still have all the other stuff I need to do. Okay, so it is not on a critical pathway that I need to factor this in. For this second multiplexer over here, for the ALU source, the reason why we do not include it is because you can see that this data is coming directly from the instruction and just going through the sign extension. Okay, sign extension, again, it is a very fast operation with just some logic gates. All right, and that tells us that this data over here would be ready at this point much earlier than the register file. And since the control unit is also going to be taking faster than the register file, I will be able to generate the correct ALU source signal and stand by the data over at the ALU ahead of RD1 being ready. Okay, so this second pathway for the immediate value is going to be much faster. So RD2 is going to be, sorry, not RD2, but the second ALU's input over here, okay, is going to be ready uh, ahead of the RD1 appearing on the ALU. All right, so because of that, we do not need to factor this multiplexer's timing, okay, in our calculation. Okay, so for lower instruction, there is a data memory access, so I need to read the data from the memory. And then finally, I go through the multiplexer and then I write back. Okay, so this is the full pathway, which takes 1300 picoseconds. For this last instruction, BEQ, so what is happening? So if I write instruction BEQ, okay, I say 3, 4, and put 8. That means I'm taking the content of two registers, doing a comparison operation, and then deciding whether to branch or not to branch. Okay, so I need to extract both RS and RT. Okay, so that is the register file. After that, I need to pass through. So in this case, the ALU source has to be factored in because only after RD2 is ready, then I can pass it through to the next stage. Okay, so register file has to be completed first, and then the mux for the ALU source has to pass through the data. Then I do the ALU, and then in this case, I have an AND gate over here. Okay, because I need to compute the branch address. Okay, and then finally the mux that will decide the PC source. That means either PC plus 4 or the new branch address. All right. So over here, okay, you see that there are two pathways that we did not factor in. One is this, to generate the PC plus 4. Okay, and the other one is this, to generate the address that I want to jump to the offset address. Okay, again, why we never factor in these two pathways? Because these two pathways are made up of blocks that can execute much faster than your register file and ALU and so on. Okay, so because of that, the data at the inputs of the multiplexer here will appear much faster, okay, compared to the time that it takes to generate the PC source signal. Okay, so because of that, you do not need to factor in the green pathway and this purple pathway. Okay, so the total time here that it takes is 800 picosecond. Okay, so this last three question is just for us to have an idea of the pathway that it takes and how we analyze the time that it takes for the different instructions to execute. Okay, so does anybody have any questions you want to ask about these last three questions here? Okay, so the PC increment by 4 is always done automatically, correct? Because that is a hardware block. Okay, this PC plus 4, this block is always done automatically for every instruction. Okay, so this PC plus 4 is always generated. Again, these are not factored in because these are all considered very fast operations that will execute much ahead of time compared to the rest of the blocks that we need to uh, take into account. Okay, so from this, you can see that the memory access instruction, okay, always takes the longest time because memory has always been the bottleneck of computing systems. Okay, so if you look at this, instruction memory access and data memory access always take the longest amount of time. All right, and I'm sure if you keep track of the way our computing systems have been evolving, our processor speeds have always gone much faster ahead than memory speeds. Okay, so that is always been the bottleneck in our systems. All right, so that is why memory access instructions will always take very long. All right, and which is also one of the reasons why uh, there's been a lot of there's a lot of research and ideas into how to improve uh, memory access, okay, or memory systems to match up to processor speed. Okay, so for memory and memwrite, okay, generally the time is different, okay, because the actual processing done within the memory is different for memwrite and for memory. All right, so the timing will be a bit different. All right, but again, in the question, if they never specify that it is two different timing, then you take it to be the same. That means data memory access is considered single timing, whether it's it or right. Okay, but practically, okay, it is actually two different uh, timings you will look at. Okay, so what I will do now, okay, so this brings us to the end of the tutorial. Okay, so what I will do now is, so don't worry, like I said, uh, I'm sure that right now you're definitely in a much better position than when we started about 2.5 hours ago. Okay, so you just need to go through the material one more time or two more times to just look at the arrows, look at the flow, okay, the control signals, what is happening, and then you will more or less get the idea of how things are working. All right, so don't be overly concerned if you still have doubts and so on. You can always email me and contact me. I will still answer and clear your doubts. All right, so what I will just want to do quickly before we end the day is to just to run through the term paper with you. Okay, so if you remember that in the beginning I mentioned there is no midterm assessment. So in place of that, there is this term paper. This term paper is actually not very difficult. It is you just need to take the last slide that we have from our last few slides that we have from our notes or from the tutorial with the whole processor design, and you now need to redesign a new processor. And the only difference, the only thing is this new processor that you're designing is having an 18-bit wide instruction. Okay, so what is the implication of this? Okay, so the implication of this is what? Let me share you the screen. All right, so previously, okay, we have 32 instructions. Sorry, 32-bit instructions. Okay, for our MIPS processor. So out of the 32-bit instructions, we said that okay, we have R type, we have I type, okay, and so on. Okay, and then we say we have opcode, okay, we have RS, RT, RD, and so on. Okay, so this is how we designed it. Okay, now what we are saying is from 32-bit, we are now scaling it down to 18-bit. Okay, 18-bit processor. So now what you okay, so what you need to do is, so now you have a smaller number of bits. You now need to decide how you're going to split them up. Okay, so let me give you an example. Okay, so if I say opcode, if I say opcode is 3 bits, okay, so you can have 2 to the power of 3 different type of instructions. Correct? Okay, similarly, if I say I support RS, RT, and RD, same as before, and it's also 3, 3, 3. Okay, that means I have 2 to the power of 3 different registers inside my system. Okay, that means I have a total of 8 different opcodes for instructions and 8 registers inside my register file. So previously your MIPS processor has 32 registers. Alright, so inside the register file, okay, previously we say it is 5 bits, 5 bits, 5 bits. Now you say it's only 3 bits. Alright, so now the data that comes out is only 2 to the power of 3. Oh, sorry, no. That is the data width. The data width, let me see, what is the data width that is specified? Data word width is your choice. Okay, so the data word width of your choice means you can decide each register is how big. So within the register file, you can decide how big is the register file. So you can still stick with the register size of 32-bit. Okay, but how many registers you have depend on how many bits you specify here. Okay, that means if I say I only have 3 bits to specify my registers, that means I have a total of 8 registers. 0, 1, 2, all the way to 7. 8 registers. But each register, I can decide whether it's going to be 32-bit, 16-bit, 8-bit. That is up to you. That is your choice. Okay. So if you look at the term papers requirements, basically you must support basic R type, I type, some basic arithmetic and logical operations. You must specify how many registers you have, and you must show the data part and control design. This part is actually nothing more than just modifying, okay, from what is already given to you in your notes. All right, the entire architecture is already given, but you now change, okay, it according to your uh, number of bits that you are setting aside for the different parts of the instruction. All right, now, so that is the processor design part. For the code, what you need to do is, so now that you are designing this own code, your own code, own processor, you are going to write a sequence of instructions that takes a number n and generates the square of the answer. Okay, and it should be stored in a memory location, and you can write back to the same memory location. Okay, so what are you supposed to do? That means you are supposed to read from some memory, correct? So inside your data memory, okay, so let's assume that inside address location 8 0x8, I take out this data, okay? Let's say this is the n, correct? I take out this data and then I pass it to my processor. So in my instruction, okay, in my code that I write, your first instruction should be I must do some load, okay, from 8 into a register. Okay, so that is the first instruction. Okay, because you are taking this data and okay, which is in address 8 and putting it into a register. So how the instruction is going to be is up to you, correct? Because you are designing this whole processor by yourself. After that, after this first instruction, the next few instruction is to okay, so this into a register means inside the register you have a value n, correct? So what you're supposed to do is you're supposed to write your own code to compute n square. Okay, and then finally you store n square back to 0x8. That should be the final instruction. Okay, so that is basically what you're supposed to write. So it's a few lines of code, but when you writing the code is one thing, you must also provide the equivalent machine code instructions. Okay, the binary instructions, and this should match your processor design, correct? So in your processor, maybe you have 3-bit for opcode, 3-bit for RS, and so on. So your machine code that you give should be matching the processor that you have designed. Okay, so there is no right or wrong particular approach here because you are designing on your own. As long as you can fulfill that, you have all these requirements, you can fulfill all these requirements, and you are able to write the instructions uh, within your own processor to perform this operation, then that is fine. Okay, so it doesn't matter whether I say I use 3-bit opcode, 4-bit opcode, 5-bit opcode, that is up to you. Okay, so that is your own design. You can decide and then put that in your report, how you have designed it, what is the justification or how it comes together. Okay, so function, shift, amount, all again is up to you to decide. All right, because ultimately, as long as you can cover some basic arithmetic. So when I say basic arithmetic, is things like your and, your or, your nor, okay, and arithmetic is just your plus and your minus, correct? Okay, and of course, you whether you want to support just register access. Okay, I mean you must support both register access and immediate value access as well. Alright, so that is why here it is stated you must support both R type and I type. Okay, so if I support add and subtract, it must be R type plus I type. Similarly for logical, if I say and or nor, for example, then it is just R type and I type for that as well. Okay, so you must support enough operations, all right, that you can fulfill the code part later on. Okay, so multiply should not be used because I mean you can put multiply, but it should it is possible to use multiply. All right, if you do that, then of course you need to just take into account how you're going to perform that. All right, but I would advise not to use multiply because you can relate better to what we have already done so far. Okay, so far in our ALU, all right, and in our MIPS, we have not used multiply instruction, correct? We have only used the add, subtract, plus logical instruction and so on. All right, so you should stick with the instructions that we have used so far. Okay, so doing n square is not that difficult. Okay, you don't need a multiply to do that, correct? It's just about repeatedly adding the same number again and again, correct? So you just need to think of it in terms of a loop, all right, and how many times to keep adding that number again in that loop. Okay, so that is basically the term paper. And to make your life easier, I have a maximum page count. So you should not write more than 5 pages. All right, so this is to keep your report short and simple and direct to the point. All right, so that you do not try to dump everything and anything inside and then create a 200-page report for this. Okay, so just keep it very simple within 5 pages only. Okay, so that you focus on what you have done, how the design how you design the processor, how your code works, and just stick to explaining those important points only. Okay, so the folder has already been created for submission. Okay, so this is again just a reminder, it's a turn it in folder, which means it will check across submissions from others. All right, so it is fine to discuss and work together. That part is fine. All right, but of course, the report, the words that you write, it must be your own, correct? Okay, even if you are creating a picture, a processor picture, you should create your own sort of design. Okay, you should not let your friend design and copy his picture and put in yours. All right, so just make sure that it's okay to discuss. Okay, but the work must still be done individually. Okay, so the deadline is end of week 12. I think it's more than enough time. Okay, for you to finish this up. Okay, so the design has to include whatever that is needed, correct? So uh, if you are having a loop, definitely you need to have branch instructions, correct? So definitely you need the control signals part for all the multiplexers. You need the uh, PC plus 4 plus that particular multiplexer as well to make a decision whether branch should be taken or not. Okay, so basically you can leverage the entire processor design that we have already been using, okay, that we saw in the last 2 lectures, and you just modify from there. Okay, so that's all I have for today. Okay, so I will upload the video plus the slides, okay, by tomorrow, and then you all can have a look, okay, and then try to go through it one more time just to make sure you understand the concepts, and that will help you with the term paper as well. All right, so I will send an announcement, okay, on what to prepare for next week onwards, when as we are starting the new half on the OS portion of the module. Okay, so I'll send you an announcement on what to prepare and what to do. So next week onwards, we will move to OS. Okay, so that is the officially we are ending MIPS today. Okay, so hope that is good news for all of you. Okay, so thank you very much. Okay, good night. I will see you all next week. Okay, for OS.